Hello, we already stated the alternating series test. This test says that for an alternating series verifying two fairly easy to verify conditions, we know that the series converges. Note that the test does not tell us to which number the series converges, but we're going to be able to get an estimate on the value of the sum of the series. But for that, we need to look into the proof of the alternating series test, and that's what we're going to do now. Suppose we have a series verifying the conditions above. So it is an alternating series, so it has the form we want for alternating series. And sorry, we start summing in 1 in this case. And also we know that these AN are positive terms, and we know that the limit of the ANs is 0 as n approaches infinity, and we know that the terms of the sequence in absolute value are decreasing, at least after some point. We are going to look at a picture showing the terms of the series and the sequence of partial sums. This is our picture. Let's say we have over here, well, our first term, let's say the value 0 is over here, and then we have our first term A1 here. Note that A1 is the same as the first partial sum. I'm going to be writing the partial sums over here. A1 coincides with S1. S2 is the sum of A1 plus the next term, so it's A1 minus A2. Remember, the terms are alternating. And we know that A2 is less or equal than A1, so that means that when we look at the value of S2, is going to be greater or equal than 0. We're going to be going back from A1 as much as the value of A2 is. So let's say we get up to here. This is A1 minus A2, which is the value of S2. And then let me show here what happened. This was our value A2. We went back from A1 to A2. Next, we are summing to A1 minus A2 the term A3, and we know that A3 is less or equal than A2, so that means that when we go forward, we're not going to go to the right of A1. We can go, let's say, up to here. So here we will have, let's just write the S because it's going to get too crowded otherwise, S3. And then let me show over here with a different color. This was the value of A3, and as I say, because we know that A3 is less or equal than A2, we're not moving to this side over here. That's not happening. Next one is 4. To the value we have already A1 minus A2 plus A3. We have to subtract A4, and when we subtract it, we do not go to the left of S2 because the value of A4 is less or equal than the value of A3. So let's say we go up to here and we obtain S4, and then yet another color. It's getting a bit crowded, but it's okay with the colors. This is the value of A4. We move to the left. Let me just draw the next step. S5 is going to be somewhere less or equal than S3, and then we're going to have S6 is going to be more or greater or equal than S4. So without writing all the details, if you see what we have over here is the sequence of partial sums. If we restrict ourselves to the even terms, we have S2 is less or equal than S4, which is less or equal than X6, and we'll get this is less or equal than S2n, which is just a generic term of that subsequence, which is going to be less or equal than the next term, 2n plus 2. So this is what's happening with the even terms of the sequence of partial sums. If we look at the odd terms, they're over here, we are going to see, well, we had first S1 and then S3 was less or equal than it, and even less or equal S5. And if we keep going like this, we'll see that an arbitrary odd term is going to be decreasing with respect to the previous one. I don't have a lot of space here, but I'll write that this is S2n minus 1 and S2n plus 1. So if we restrict ourselves to the subsequence of odd terms, this is a sequence that is decreasing. Intuitively, what is going to happen is that, let me use sky blue for the even ones, they're going to be going up, and let me use red for the odd ones, they're going to be going down, and there's going to be in between the two of them, new color, here, there is going to be here the limit we are looking for, S. Okay, how can we show that that S actually exists? Let me write here what we have so far. We have the sequence of the even terms of the partial sum of the series we're trying to sum, and we know that this sequence is increasing. I'll symbolize it with this arrow going up. We also know that all the terms we have in the sequence, they're all less or equal than, let's say, A1. Yeah, we know that we moved from the left from A1 and then we can never move back to the right. So what we are saying is that the value A1 is a bound for the sequence we have over here. Let's look at the sequence of the odd terms. S2n plus 1. This sequence is decreasing. Yeah, I'll symbolize this with an arrow going down. And we can also find a bound for this. In this case, it's going to be a lower bound. So there is a value that is less or equal than all the values of the sequence. And we can take as this value, for instance, the term S2 of the sequence. Yeah, that was the second of the partial sums. We know that with the third one, we move from the right from there, and we're never allowed to move back to the left. So this sequence is decreasing, has a lower bound. So with that picture very small over here, we have a bound and we have a sequence that is always increasing. And here we have a similar kind of mirror situation when we have a bound and we have a sequence that is always decreasing. Okay, so there is a very important theorem that says that these kind of sequences that are either increasing with an upper bound or decreasing with a lower bound actually do have a limit. The result I'm talking here is called the monotone sequence theorem. Let me write it over here in this little space. Monotone sequence theorem. And what it says is the following. Let's say we have a sequence Cn, and we know that these terms Cn are increasing, and we know that they are all bounded above by a same value, let's say k. Then it exists the limit of the sequence Cn, and let's say we call it L. It doesn't have to be k itself, but it exists. Similarly, if we have a sequence Dn, and in this case the sequence Dn is decreasing, and we also know that it has a lower bound, let's call it a value, I don't know, t, so t is less or equal than all the terms Dn, then we know that the sequence Dn is convergent, so the limit of Dn as it approaches infinity, I didn't write it here, is some value, I don't know, let's call it r. Doesn't have to be t itself, but we know that it exists. This very important theorem applied to our case with the sequence of the even terms and the sequence of the odd terms means that the limit of the, let's say first, the even terms exists, and let's call this value, I don't know, L1, and also the limit of the odd ones as n approaches infinity exists, and let's call it L2. So in a picture over here, so far we have the even terms going up and having a limit L1 over here, the odd terms going down and having a limit L2 over there. Our next goal is to prove that actually the values, this is what we want to prove, the values of these two limits, L1 and L2, are equal, and then in this case, they will be just the limit of the sequence of partial sums, so they will be the sum we are trying to show that it exists. So let's prove that the two limits coincide. So far what we have is that any of the even terms of the sequence is less or equal than the value of the limit of that sequence, so L1, which has to be less or equal than L2, and this has to be less or equal than any value of the sequence of the odd terms. Let's just pay 1 second attention to the middle inequality we have over here. Well, it has to be the case that the limit of the L1s is less or equal than the limit of the L2 because of the inequality that we have with the term. Now, the difference between the terms in the middle, the L2 minus L1, has to be less or equal than the difference between the terms on the side. There is more space there. Yeah, but this distance, it's exactly an plus 1, which is approaching 0. And since we know that the difference between the limits has to be positive, we say that the L2 limit is greater or equal than the L1. By the squeeze theorem, we know that actually L2 has to be equal to L1, and this is the sum we were trying to prove that it exists. Now, this is going to give us a very useful result, altimeter series estimation theorem, that is going to tell us that when we have an alternating series convergent because it satisfies the two conditions of the alternating series test, then we can estimate the sum of the series using the n partial sum and knowing by how much we are making a mistake. So I kept over here our inequalities from before, and let's see how we use them to obtain the result we have over here, that in absolute value, the difference between the sum we are trying to find and the nth partial sum is less or equal than the next term of the sequence. So from the proof of the theorem, we know that any of the even terms of the partial sums is less or equal than the sum of the series, which is less or equal than any of the odd terms of the sequence. So if we look at the difference between the sum and any even term, we don't need absolute value here. This is going to be less or equal than the difference between the odd term and the even term, which is exactly the term an plus 1. And in this case, we are done proving this inequality. On the other hand, if we, with the partial sum we want over here is an odd term, we don't know, it could be, I'm going to write that actually s2n plus 2 is less or equal than s is less or equal than s2n plus 1. And that's also true because I say all the even terms are less or equal than the sum, less or equal than any odd term. So now when I look at the difference between the sum and the odd term, in this case I do need the absolute value, but it's going to be less or equal than the difference between s2n plus 1 and s2n plus 2, and that difference is exactly the term a2n plus 2, as we wanted to prove. So in our next video we'll see how we can apply this estimation.